All right. Sorry about the slightly late start, but we'll get going now. Um, Something that I know you've been asking, wanting clarity on, those two extra assignments we have to do for communication and teamwork. Um, so the communication thing, I'm in the process of making it. It'll be done in Canvas, so I'll send out information by email about that. That's probably the only assignment we'll have that's done directly in Canvas because I don't have the access and WebAssign to create assignments there, and I'm also too old to learn a new platform, so we're gonna do it in Canvas. It'll just be like a pretty short thing where you'll have to not just give answers, but actually explain how you would get the answer. That's how we're going to evaluate communication for this. Because there's a lot of you and I have to grade it by hand, it's going to be pretty short, and I'm not going to grade it with a fine-tooth comb, but you guys all have to do it if you want to get that 1 point on your grade, 1% of your grade. And then for the teamwork thing, again, details still to be worked out, but I will plan to do that on the very last day of class, which for us is April 24th. So the 28th is the very last day of the semester, but since we're a Tuesday, Thursday class, the 24th will be the last time that we meet. So that'll be in class. So you have to be here for that. And I'll, again, send more information about that to make sure everybody knows. But that's going to be coming up in about 2 weeks. All right, but what we have to do before that is we have to cover and finish the very last chapter of our textbook. So everything we cover today will be part of still the third exam. So chapter 9 is kind of divided in half. Everything today is still at the beginning parts of that. So this will be all third exam materials. And what chapter 9 deals with, the very last topics we'll cover are the other two phases of matter. So chapter 8 was all about gases. This is all going to be about liquids and solids, starting with liquids. And what you'll see in chapter 9, as I've told some of you that have asked about it, it's very, very qualitative, so kind of more like chapter 4 in some ways. There's really no equations, or just one, I think, that we have the whole chapter. It's not a lot of depth. There's a lot of different topics we cover, but not very much depth to it. So you'll see that as we go along. All right, so let's get into it. And the first thing we want to do is sort of compare and contrast things that we just learned in chapter 8 to what's going to be a little bit different when we're starting to talk about the condensed phases, liquids and solids. So for ideal gases, we just covered the kinetic molecular theory last class, and one of the key assumptions was that the gas particles, the atoms or the molecules that make up a sample of a gas, have no interactions with each other. So that was one of the key assumptions that explains how gases behave, the idea that there's no attraction between the gas atoms or gas molecules, there's no repulsion, they're just kind of flying around independently. Now, the reality, though, is if you're dealing with a real gas, so something that's not in the ideal situation, but in real life, or the other two phases of matter, liquids and solids, whatever makes up those substances, those atoms and molecules are going to be in constant contact with each other. In gases, this contact is minimal, which is why they behave as gases, fly all over the place, fill up all the available volume that they have. That's why they behave like a gas, but there is still some contact between them. And the reality is that, and it's particularly pronounced in liquids and solids, there's going to be attractive forces between the atoms and molecules that hold everything together. So we know that if you have a liquid or a solid substance, it doesn't just move everywhere to fill up the available space. It's confined to a specific volume. Liquids can change their shape, but not their volume. Solids are both fixed shape and volume. And the reason for that is that the atoms and molecules that make them up are held together by these forces. They're not allowed to just fly everywhere like they are in a gas. So that's, again, particularly relevant to liquids and solids, where the atoms and molecules are in constant contact and they're held together in that way. Now, one thing I want to point out many times to make sure we understand the distinction is that when we talk about the attractive forces that hold together liquids and solids, we're not talking about chemical bonds. We're not talking about the bonds that hold two atoms together in a molecule, or two ions together in an ionic compound. What we're talking about here are if we have two or more different molecules, the forces that would hold those two together. So they're not nearly as strong as a chemical bond, and they're not actually involving sharing of electrons or anything like that, but they're going to be attractive forces that allow separate molecules to stick together. Okay, so it is different than what we learned before, and I want to keep emphasizing that to make sure we get the distinction. So the term that we use for this is intermolecular forces. So in a lot of fields of science, there's knowing a little bit of Latin is helpful, even though Latin is not taught very much anymore. And so from the Latin root, inter means between. Intra means within, inter means between. So when we're talking about intermolecular forces, those are the forces that hold two molecules together. And so again, these are going to be attractive forces that we're talking about that cause them to stick together. And the key word is that it's between two molecules. Yeah. Yeah, go ahead. Um, or more generally, this is between, they don't have to be molecules, I suppose. So a collection of atoms will have still what we call intermolecular forces, even though they're not made up of molecules. Um, but they're forces that hold things together, whether they be atoms or molecules in a condensed phase, especially. Um, so remember that what we're going to contrast that with is these intermolecular forces have nothing to do with chemical bonds between atoms. Those would be called intramolecular forces. So again, inter versus intra. Intra means within, and those would be the forces, the bonds that hold things together in a single molecule. Intermolecular forces are dealing with forces between two or more molecules that are together. It also has nothing to do with covalent bond strength. So we learned back in chapter 3 how to predict relative strengths of covalent bonds based on the length of the bond order, things like that we already talked about. But again, when we're talking about covalent bonds, these are also intramolecular forces. So all that is to say, if we're going to learn today how to predict the relative strengths of intermolecular forces. We're going to learn how to predict the relative strength, and it has nothing to do with the types of bonds that the substance has or the bond order or anything like that. It's totally separate from that. It's just the force of two different molecules or two different atoms sticking together in a condensed phase. Now, one thing we have to also then understand as we start talking about these intermolecular forces is, what key properties do they influence? Why do we need to know about them? Why do we need to think about them? And one thing that we're going to often think about in the context of intermolecular forces, there's a few other properties we'll talk about, but a big part of this is going to deal with what are called phase changes, which is converting a substance between two different phases of matter. So we're going to talk about this in more detail later on, but as we introduce intermolecular forces, one of the key things we're going to focus on is how do those intermolecular forces affect these phase changes, and in particular, the temperature at which these changes occur. So we're going to talk about conversions between liquid and gas phase. So in that direction, it's referred to as boiling or vaporization. Boiling is when you heat up a liquid to convert it entirely to the gas phase. Vaporization is a spontaneous process that occurs with liquids where some of the molecules will evaporate into the gas phase. So those two are related. It involves liquid molecules converting into gas phase molecules. The opposite process from a gas to a liquid is referred to as condensation. And then the other phase change that we'll at least talk about today is converting liquids into solids or vice versa. So the liquid to solid transition is referred to as freezing, and the solid to liquid is referred to as melting. So those are terms you've likely heard before, but what we're going to talk about today is how the intermolecular forces in a substance influence the temperature at which these transitions would occur. So we call those temperatures the freezing or melting point or the boiling point. Oh, sorry, what is this? So the freezing point or melting point is where this transition occurs. I forgot to write out the first one, which is the boiling point. So those are the temperatures at which these phase changes go to completion. We're going to give more precise definitions for them later on, but for now, this is all we really need to think about. So the boiling point is the temperature at which a liquid converts to a gas completely. Again, there's always going to be some vaporization of the surface, but if you want to drive it completely to form a gas, and we're going to give a more precise definition for that later, but that's fine for now. And then freezing or melting point is the temperature at which liquids and solids interconvert. If it's going, again, from a liquid to a solid, you would call that melting. Usually melting point is the term we use more often, but you can go in the opposite direction as well, from solid to liquid. Sorry, solid to liquid is melting, liquid to solid is freezing. We use those terms kind of interchangeably. And the key thing that we're going to then talk about and how it relates to intermolecular forces is that the stronger the intermolecular forces you have, we're going to use the abbreviation IMF for intermolecular forces. Doesn't mean International Monetary Fund in this course. It means intermolecular forces. So the stronger intermolecular forces you have correlates to higher boiling or freezing points. I'm going to say melting points. That makes more sense in this context, even though they're the same temperature. All right, so the stronger the forces that are holding the atoms or molecules together, the more heat, the higher temperature you have to acquire to be able to cause them to separate. So if you're going, again, from liquid to gas, you have to go to a higher temperature to boil them, or if you want to go from solid to liquid, a higher temperature to sort of separate those molecules from the solid phase into the liquid phase. All right, so then to be able to make predictions about which substances have stronger intermolecular forces, we need to talk about the different kinds of intermolecular forces that we have and what factors affect how strong they would be. So the first type of intermolecular force we're going to cover is called London dispersion forces. I believe it's named after a person and not the city, but nonetheless, they're called London dispersion. And the thing with London dispersion forces is that every substance has them. So one thing we're going to have to be able to sort of categorize and predict are, if I have a specific substance, what type of intermolecular forces are involved. And so with London dispersion forces, though, everything has them. So all compounds, all substances, I should say, probably even better to say substances because not just compounds, any element or compound. So anything with electrons has London dispersion forces. Of course, every substance has electrons, so that goes without saying. Now, what are these London dispersion forces? We're going to try to describe them a little bit here, but what they involve are what are called instantaneous dipoles. All right, so if you have a monoatomic element like helium, now clearly in helium it can't be polar. It's only a single atom, but there's no bonds involved at all. So you can't say that the substance is polar. But what you have in any substance, including helium, would be what are called instantaneous dipoles. So if you have a helium atom, as we sort of talked about back in chapter 2, when we talked about electron configurations, the electrons in helium are symmetrically distributed around the nucleus. They're both in a 2s orbital. On average, that 2s orbital has a spherical shape, so everything is sort of symmetrically distributed. There would be no dipole in that situation. However, as we also learned in chapter 2, when we talk about the shape of an orbital being spherical, that doesn't mean the electrons are in that same space all the time. There's a probability of finding them in different locations, and you're always going to have a little bit of an oscillation of the electron density. Even though it's spherical on average, it's going to be sort of wiggling around because of that probability, because of that wave function. So at some snapshot in time, what you might have would be a situation like this, where in one helium atom, the electron density is kind of skewed in one direction. This is what's called polarization, the idea that the electrons are not held firmly in place, but they're kind of moving around kind of like a blob, an ill-defined blob, even though the average shape is spherical. And what that leads to then is a situation where this helium atom has a slight uneven distribution of its charge, partial positive, partial negative charge, because of the electron density being not spherical around the nucleus for that instant in time. And then that can attract to another helium atom that has the opposite polarity. So if you have this situation here, the opposite charges line up. And what you actually have occurring sometimes is called induced dipoles, where one atom that for a brief instant has a small dipole comes in contact with another atom and pulls electron density from that atom towards itself, so that because opposite charges attract each other. And then this is not a static picture though, so then this is going to oscillate in the other direction. And it's going to then line up with the helium that's polarized in the opposite direction as well. So you get these oscillations in electron density where even though on average it's totally spherical, totally nonpolar, for brief periods of time, there's an uneven distribution of the electrons, and that leads to a small attraction between the atoms. All right. And helium is very small. There aren't very many substances that have weaker intermolecular forces than helium. Might be the weakest, or maybe hydrogen is a little bit weaker, but nonetheless, you have these small forces of attraction. It's not a zero force of attraction. And then if you have molecules, even if the molecule is nonpolar, so we would have predicted that Br2 is nonpolar, and it is, and that's not false. It's not a false statement, but Br2 is nonpolar because it has two of the same atoms bonded to itself. It's a perfect covalent bond. And what we would then say about the electron density is that on average, it's going to be symmetrically distributed around the two bromine atoms. So if you had two completely nonpolar bromine atoms lined up with each other, if that was sort of the static picture there, you wouldn't expect them to have any force of attraction because the electrons are perfectly symmetrically distributed. There's no dipoles involved. But for the same thing that happens in helium, these electron clouds distort over time. They're not static. They're oscillatory in some nature, and the electrons are not strongly held necessarily, so they move around. And so you're going to have brief instances in time where the electrons would be unevenly distributed around the two bromines. So something like this, I'm going to try to exaggerate a little bit, where the electron density would be skewed towards one side of the molecule, giving a partial negative charge on that side. And then if it lines up with a Br2 molecule that's polarized in the opposite direction, where its electron density is skewed over here, the opposite charges are going to line up with each other, and they're going to have a small attraction. And again, this is not a static picture, so it sort of oscillates in all directions. You're going to have this situation then as well, where you're going to have more electron density over there. I didn't do that very well. And then that's going to line up with another bromine that has its electron density skewed in that direction. And again, you're going to get these opposite charges sort of lining up and attracting to each other. So these little dashed lines mean. So that's how London dispersion forces work. And every substance, even if it's just atomic like helium, or even if it's a nonpolar molecule, is going to have those London dispersion forces. So if you're comparing then a bunch of substances where this is the only type of intermolecular force, as we'll get into in a little bit, this is the weakest of the possible intermolecular forces that we have. And again, because you're not dealing with real dipoles here, you're just dealing with very brief distortions of the electron density that lead to these small attractions. So then if you have a series of substances where London dispersion forces are your only forces, how do we decide which of those has the strongest intermolecular forces? So let's look at the boiling points of all the noble gases. So we're going to move from top to bottom. That's the order that these are written in, helium down to radon. So helium has a boiling point of 4 Kelvin, exceptionally low, not very much above absolute zero. And as we go down to neon, which is heavier, the boiling point gets bigger. Argon goes up to 87 Kelvin, krypton 121 Kelvin, xenon 165 Kelvin, radon, the heaviest noble gas, all the way up to 211. So you can see there's a pretty big increase in boiling point as the noble gases go down the column, which means as they get heavier and heavier, as they have more electrons in them. All of them are still gases. 211 Kelvin is still below room temperature. So it would be a gas at room temperature, but it's higher, much higher than helium, which is 4 Kelvin. So the conclusion we can draw from that, and this is really the main thing you would need to know about London dispersion forces, is that London dispersion forces are stronger when there are more electrons. So that means if the atoms or molecules are heavier, and they have higher molar masses, there are more electrons in them, you're going to get stronger London dispersion forces. So that would be true for simple atoms like the noble gases, or if you move down the diatomic halogens from F2 to Cl2 to Br2 to I2, those intermolecular forces get stronger and stronger. And that's why, as you remember from the standard states of elements, F2 and Cl2 are gases. They have relatively weak intermolecular forces. Br2 is a liquid. It has stronger intermolecular forces because it's heavier. So it's held together as a liquid. I2 iodine is a solid. So that kind of matches with that as well. And what this sort of relates to then is what's called the polarizability of the substance. Polarizability is the ability of an electron cloud to distort. So as we said, in nonpolar substances, the electron cloud, the electron density, is on average totally symmetric about the nuclei, but it does distort because of the electrons and the outer electrons especially not being very tightly held. So because the outer electrons are held less tightly, that allows them to distort. And as you go to larger and larger atoms, those outer electrons get further and further away from the nucleus. They occupy subshells that are larger and larger on average, and that gives them a greater ability to distort. So that's why as the atom gets heavier and heavier, the London dispersion forces get stronger and stronger because those electrons get further and further away from the nucleus, they're able to distort more. So in larger atoms, the outer electrons are held less tightly. So that means heavier atoms, those that have more electrons, are more polarizable. Now, one other thing that I should probably point out, I don't think I have an example problem on this. Well, let's just do this one first. So this is an easy one. Rank the halogen molecules from lowest to highest melting point. Kind of already talked about this, let the cat out of the bag. But we have halogen refers to the second to last column of the periodic table. They're all diatomic in their standard state. So remember that if we want to have a higher melting point, in this case, we're talking about melting point, but whether it's talking about melting point or boiling point, those are going to be higher when the IMFs are stronger. And these are all nonpolar substances, so London dispersion forces are the only type of intermolecular force we have to think about. And those are going to be stronger in heavier elements, as we just finished talking about. So then now, surprisingly, as you move down the halogen series from the lightest one, which is F2, to the heaviest one, which is I2, their melting points or their boiling points are going to fall in that exact order. So there's not a whole lot to this one. If you're dealing with nonpolar substances with London dispersion forces, all you need to think about are how big they are, how heavy they are. Now, there is one other thing that sometimes comes up, and I want to just discuss it here briefly because sometimes it shows up on assignments and I haven't talked about it, and it leads to some confusion. The other thing that can affect the polarizability and then the strength of the London dispersion forces is the shape of the molecule as well. And where that'll kind of come into play is going to be so a very common class of nonpolar substances that you'll see are called hydrocarbons. They're compounds that have just carbon and hydrogen in the formula. We've seen them in other contexts before. And one thing we probably mentioned way back in chapter 4 is that those substances are always nonpolar because there's going to be no lone pairs on the carbon. All of the CH dipoles, which are small to begin with, are going to be symmetrically distributed and they're all going to cancel out. So any substance that's a hydrocarbon is you can already predict it's going to be nonpolar, and you can already predict then that London dispersion forces would be the only type of intermolecular force involved. But sometimes when you're comparing compounds like that, if you want to know which one has the stronger IMFs, higher boiling point, higher melting point, consider this situation here. Let's say we have two isomers of what are called pentane. So one would be a linear form where all the carbons are just in a linear chain. So 5 carbon atoms in a chain. Another isomer of pentane in the opposite extreme would have 1 carbon at the center and then all these different carbons coming off of that. And you're asked to predict which of these substances has either the stronger intermolecular forces or the higher boiling point, let's say. And you can't really do that in this case just on the basis of which one's heavier. These two compounds have exactly the same chemical formula. They're all C5H12. So they have the same molar mass, same number of electrons. So that's not going to factor in here. But what does factor in is the shape of the molecules. So when you have a molecule like this that's linear, in reality it's zigzag, but it's all in a chain that's sort of elongated. Those are going to be able to pack together more tightly and have stronger forces of contact because the molecules are more or less flat and they have a higher surface of contact with each other. So this is going to be more polarizable or have stronger intermolecular forces. Versus this one here, which is approximately spherical in shape, not really spherical, but is 1 carbon at the center with 4 around it, so it's more like a ball. Those can't pack together as tightly, and they don't have as strong of forces of contact because there's just not as much surface area in the molecule that can engage in those intermolecular forces with other molecules of the same type. So sometimes you are asked to consider the shapes of molecules, and it really won't come down to things that are more complicated than this, but I just wanted to make sure that I pointed that out since it comes up sometimes. All right. Now, the next type of intermolecular force we have to talk about are dipole-dipole forces. So we're going to give a final ranking later on, but dipole-dipole forces are stronger than London dispersion forces. And typically when you're this word here, spherical. So this molecule is not really a sphere, but it's like 1 carbon at the center with 4 around it. So it's kind of like a ball shape overall. So it doesn't pack together with as much surface area of contact as you would in a linear sort of chain shape like that one. All right, so then what we have are the next type of intermolecular forces are dipole-dipole forces. Typically, when you're making predictions about the properties of molecules and as they relate to intermolecular forces, you mostly want to think about what is the strongest intermolecular force that that molecule has. So for the ones we just talked about that are either single atoms or nonpolar, they only have London dispersion forces, so that's the only thing to think about. For anything that has dipole-dipole forces, they're going to also have London dispersion forces, but the dipole-dipole forces are significantly stronger, so those are going to be the ones that really are key to predicting any properties that would come from that. Dipole-dipole forces are still a lot weaker than chemical bonds. They're about maybe 1% as strong as bonds. So if you think about, carbon-hydrogen bond is like about 400 kilojoules per mole bond strength. The strength of a dipole-dipole force would only be about a few kilojoules per mole. It's much smaller, but it is still larger than the London dispersion forces. Now, which molecules involve dipole-dipole forces? This is going to be any polar covalent compound. So we learned back in chapter 4 how to predict whether a molecule is polar or nonpolar. So any polar covalent compound will have dipole-dipole forces as forces of attraction that hold those molecules together. And again, the key here is that it must have molecular polarity, it must be polar overall. not just have polar bonds. Because we did see a lot in chapter 4 that there are many compounds where the bonds are polar, but because of the way those bonds are arranged around the central atom, the whole molecule itself is not polar. So when we're talking about dipole-dipole forces, you're talking about a molecule that has net polarity, that has a net dipole moment. All right. So the way that you can rationalize this is a little bit easier to picture than it was with London dispersion forces, because in molecules that are polar, we know that there's going to be already an uneven distribution of the charge. That's what it means to be polar. So as a simple example, if you have this diatomic HCl here, fluorine is more electronegative than hydrogen, so we would have learned back in chapters 3 and 4 that this molecule would have a polarity where there's going to be a partial negative charge on chlorine and a partial positive charge on hydrogen because of the greater electronegativity that chlorine has. And then this is going to line up then and interact with other molecules that are arranged in the opposite orientation. So this delta minus can align with another hydrogen that's delta plus. So the opposite charges are going to be the ones that attract each other. And then you would have molecules that can line up in this way. So these dipole-dipole forces or any intermolecular forces are going to be going in all directions. They're not just necessarily two molecules together, but they're going to form these networks that involve these dipole-dipole forces going in all ways, especially as you get to the condensed phases, liquids and solids, where the molecules pack more tightly together. So you get all these different attractive forces. Now, the other thing that you can also maybe recognize is that you're going to have repulsive interactions between the atoms that have the same partial positive charge. So I'm going to draw in red here the idea that you can have repulsions between those that have the same charges as well, but those are going to be minimized. So the molecules are basically going to pack in a way, they're going to arrange themselves in a way that maximizes the attractive forces shown in blue and minimizes the repulsive forces shown in red. So the atoms that are the opposite charges are going to get as close to each other as possible to maximize those types of forces. So again, red here is going to be a repulsion between like charges. Blue is an attraction between opposite charges, but in that there's going to be an attraction because the molecules are going to align themselves in such a way to maximize those attractions, minimize the repulsions, and so that's going to cause the molecules to stick together and stick together with a stronger force than you would see if they were nonpolar. So polar molecules have stronger intermolecular forces because dipole-dipole forces are now involved. And then the other type of dipole-dipole force we're going to talk about, which has its own classification, is called a hydrogen bond. So in terms of how a hydrogen bond works, it's no different than a dipole-dipole force. It's just partial positive, partial negative charges lining up with each other. But hydrogen bonds, we give them a special name because they're a particularly strong type of dipole-dipole force. So hydrogen bonds can be, in some situations, around 5 to 10% as strong as a chemical bond. And if you've taken biology, you probably know that hydrogen bonds are very important in biology as well. But I want to make sure I emphasize that there's nothing really different about them. They're still dipole-dipole forces, but they're just particularly strong. And they occur in certain compounds. Now, when do they occur? The way that you can identify a compound that has hydrogen bonds is going to be one where you have a bond, and it has to have hydrogen, of course, that's what the name tells us. And that hydrogen has to be bonded to either fluorine, oxygen, or nitrogen. So basically, a bond between hydrogen and one of the three most electronegative atoms on the periodic table is going to give a large polarization in that bond. Moreover, since hydrogen is small, that allows those dipoles to pack together really closely because it's a small atom with a large partial positive charge. So basically, you look for molecules that have either a bond between hydrogen and fluorine, which would just be HF. There's really no other molecules that have that, but HF itself. Any compound that has an OH bond, So water is a classic example, but there's also a lot of other substances that have bonds between hydrogen and oxygen. Those would have hydrogen bonding interactions or bonds between hydrogen and nitrogen. So these are fluorine, oxygen, nitrogen are the three most electronegative elements on the periodic table. And so when hydrogen bonds with them, it's going to be a very polarized bond with a significant amount of partial positive and partial negative charge separated across that bond. And because hydrogen is so small, those dipoles pack together really closely. Both of those make it a particularly strong type of dipole-dipole force. Now, what I want to make sure I emphasize, though, is that the hydrogen bond is not this bond. The hydrogen bond is the attraction between two different molecules that have those bonds in it. So you identify whether there's hydrogen bonds by virtue of having an HF, HO, or HN bond, but that bond itself is not the hydrogen bond. The hydrogen bond will be the force of attraction between two molecules that have these bonds that are lined up with their dipoles and are then strongly attracted to each other. So substances that involve hydrogen bonds would be HF itself, as we said. Water is the classic OH hydrogen bond. Alcohols, so methanol, ethanol, things that end with OH in the formula. Those have hydrogen bonds. Ammonia, NH3. So basically, any compound that has one of these types of bonds in it will have the ability to form hydrogen bonds. All right, now the last intermolecular force that I'm going to cover, we don't really see a lot in this chapter. It's going to come into play more at the beginning of Chem 2, but just to be aware that it also exists and is sometimes classified separately, even though we're not going to really see it in any of our problems, would be these would be ion-ion forces. This is kind of a gray area, whether we call this an intermolecular force or not. This is usually classified as an ionic bond. It's just the attraction between two fully charged things. So like Na plus, Cl minus. So we would just call that an ionic bond, even though it's kind of like an intermolecular force because it's two different ions attracted to each other. And as we'll talk about when we talk about the structures of ionic compounds, those attractions between positive and negative ions go in all directions. It's not just two things stuck together. It's a whole network in 3 dimensions that has that. So I want to make sure we're aware of that, but even though it's not going to really be classified in the same way. And then something you'll see in the beginning of Chem 2 is that what also can sometimes happen is if you have mixtures of substances together, they can introduce new types of intermolecular forces that the individual substances themselves don't have. So one would be called ion dipole forces. And again, this is not really a topic for this course. I probably should just take this slide out, to be honest, but guess you can't teach an old dog new tricks. So I've been keeping the slide in here forever, even though I probably don't need it. Interactions between polar molecules and ions. So when you dissolve an ionic compound in aqueous solution, this is where you'll commonly see this. But chapter 9 in our book doesn't really cover mixtures at all. So this won't really come up here. It'll be something that you'll see in the beginning. But just to start thinking about it a little bit, since we have some of the key concepts now. So if you have water molecule, which is polar, has partial positives on hydrogen, partial negative on oxygen. When you dissolve sodium chloride in that, you're going to have, this is what's called an ion dipole interaction, where the positive ion, the sodium, is going to interact with the partially negative oxygen. And then the chloride that would be in there for sodium chloride, it would be, sorry, that's just H, not OH. You would have that interaction between the partially positive hydrogen. And these are going to be stronger than dipole-dipole forces because the ions are fully charged. All right. So those ion dipole forces are really only involved in mixtures, and you don't really cover mixtures until chapter 10, which is the first part of Chem 2. So don't worry about that too much, but it is related to what we're talking about, so I wanted to briefly introduce it. So then finally, what's important for us to consider are the ranking of intermolecular forces. And I'll leave out that last one because, again, it only occurs in mixtures, and we're just talking about pure substances here. But basically what you have is, and we've kind of already been mentioning this as we go along, dispersion forces are the weakest. followed by dipole-dipole forces, and then hydrogen bonds, which are a special type of dipole forces, are the strongest. So in pure substances, especially covalent substances, where this topic comes up the most, these are going to be the only types of intermolecular forces, and this is the order in which they would be. So weakest is dispersion, strongest hydrogen bond, dipole in the middle. As I kind of already said, when you're making predictions about properties of these compounds that would depend on these intermolecular forces, yes, so boiling point, melting point, or a couple other properties we're going to talk about here in a little bit, what you really want to think about mostly is what is the strongest type of intermolecular force that substance has. That's going to dominate the properties that you would observe. So dispersion force is present in everything, but if that substance has dipole-dipole or hydrogen bonding interactions, those stronger forces are going to be the ones that are more important to think about. All right, so let's just do a couple example problems that relate to this. So we want to compare the boiling points of carbon dioxide and carbon oxygen sulfide, COS, which has the higher boiling point. All right, so if we draw CO2, what we would come up with from stuff we learned way earlier in the course is that CO2 is a linear molecule, 2 carbon-oxygen double bonds. And if you want to draw the lone pairs, that's fine. You don't need them for this exercise. All right, so that's carbon dioxide. Now, both of the CO bonds are polar. There's a delta minus there, really 2 delta plus from carbon because it's delta minus on each side. But the 2 bonds dipoles cancel each other out. So this substance we would predict is nonpolar, based using the arguments that we learned in chapter 4. If it's a linear molecule and if the 2 bonds are the same, then it has to be nonpolar because the 2 dipoles are 180 degrees apart and they cancel each other out. So because CO2 is nonpolar, if we're comparing boiling points, we want to think about what are the types of intermolecular forces that would be involved. So any nonpolar substance is only going to have London dispersion forces. All right, so CO2 only has London dispersion forces. Now, if we go to the other one, which is COS, carbon's still the central atom. It looks very similar. It's still linear, still has 2 double bonds. But what we see here is that the carbon-sulfur bond is not very polar at all. I think nominally they have almost the same electronegativity values. Sulfur might be a little bit more electronegative than carbon, but it's really not that different. So it's a very small dipole here versus the rather large dipole there. So in this case, because it's a linear molecule with 2 different types of bonds, the bind dipoles don't cancel each other out. Whether you realize the direction of the dipole or anything like that, we did learn back in chapter 4 that if you have a linear molecule with 2 different outer atoms on it, it's going to be polar. So there's going to be a net dipole pointing towards oxygen still, because the dipole involving carbon and sulfur is not big enough to cancel that out. So this molecule would be polar. So because it's a polar molecule, we would predict that it also involves dipole-dipole forces. Still has London dispersion forces. Those are always there. But it has, in addition to that, it has the stronger dipole-dipole forces available. So because dipole-dipole forces are stronger than London dispersion forces, we will predict a higher boiling point for this substance because it's the polar one. So when you're comparing substances on the basis of intermolecular forces, if one is polar, one is nonpolar, you would typically make the prediction that the polar substance has the higher boiling point. If they're very different in their molar masses or the number of electrons they have, then that might get thrown off, but we wouldn't really ask you to do that. But in this case, 2 very similar molecules, one is polar, one is nonpolar. The one that's polar should have the stronger intermolecular forces and the higher boiling point. All right, so any questions on that? Yeah. This one? Yeah. All right. Anything else? Okay, so then the next thing we're going to talk about that also relates to intermolecular forces are some properties of liquids that are sort of determined by the types of intermolecular forces that they would have. And this is really all we're going to talk about with liquids. There's, liquids as a substance. We didn't really get into this a lot, but at the molecular level, liquids are molecules that are in close contact with each other. They're kind of all like rolling around each other. So there's a lot of motion involved, but they don't separate from each other like they do in the gas phase. So liquids don't really have a lot we can talk about in terms of regular order, regular structure, because the molecules are just kind of amorphously rolling around, not really anything. So the whole point of this is that the discussion on liquids in this chapter is going to be rather brief, and we're going to mostly finish it today. Most of at least over half of this chapter is going to be on solids, where there's a lot more we can talk about. But the first thing we're going to talk about are some of the key properties that liquids have. So one of them is called surface tension. This is the resistance of a liquid to increase its surface area, is one way to define it. Now that definition is not very visually satisfying, but we've probably all experienced surface tension in some context. So the idea that if you're really careful, you can get a penny to float on top of water, even though the penny would normally sink in water, but because there's that tension on the surface, if you carefully place it there, or certain insects, even though they're more dense than water, can sort of walk on the top of the water because there's that tension on the surface. And the reason that you have this surface tension is that if you think about the intermolecular forces, those are forces of attractions between the molecules. Molecules that are in the middle of the water, they're going to be pulled in all directions equally. There's going to be forces in this direction, forces in that direction, all kind of equally dispersed around the molecule. But the molecules at the surface, they don't have any more molecules above them. So in that, those are going to be being pulled down by the intermolecular forces. They're at the top. There's nothing above them to pull up on them. So the net intermolecular forces for the surface molecules is going to be downward, and that creates a little bit of tension at the surface where they're not able to spread out any further because of that. So that gives rise to what is called surface tension. Now, really, all of these properties here that we're going to talk about, pretty much all of them scale directly with intermolecular forces. So if you're making a comparison about which liquid has higher surface tension, the one that has the stronger intermolecular forces would have the higher surface tension. They all kind of scale in that same way that we're going to talk about today. So water has pretty high surface tension because it has two OH bonds, a lot of hydrogen bonding interactions that are relatively strong, and that gives water the surface tension. Versus if you were to look at the surface tension of gasoline, which is mostly nonpolar, it would be much smaller. All right, another property of a liquid that arises from its intermolecular forces is called capillary action, which is the spontaneous rising of a liquid in a glass tube. And then related to capillary action is the idea that when you look at the surface of a liquid in a glass tube, sometimes it's going to be convex, which means it's sort of buckled up like this. Sometimes it's going to be concave, which means it has an indentation at the surface. And the reason that you get capillary action and the reason that you get these different types of concave and convex surfaces is because of a competition between what's called adhesive and cohesive forces. So adhesive forces are going to be the force of attraction between the liquid and one thing that may not be obvious is that glass is polar and has hydrogen bonds. So the surface of glass is mostly like silica. So it's like SiO2, but it has a lot of OH groups on the surface as well. So there's a lot of hydrogen bonds as well. So water can attract pretty strongly to the surface of a glass. And that's one of the reasons why it would have capillary action where the water would rise through the glass because it's attracting to the surface. You really have to do that now? And then apparently planning construction schedules around classes is too high of a function for us here. So, all right. So then cohesive forces are the actual intermolecular forces of the liquid itself. So that's the molecules themselves sort of sticking together. So when you put a liquid into a glass container, you're going to have both of those forces, the intermolecular forces that the liquid experiences on its own, plus whatever forces of attraction the liquid experiences with the container that it's in. And you're going to have sort of a competition between those two that's going to dictate whether it's a convex or a concave surface. So in a convex surface, the cohesive forces are greater than the adhesive forces. So that means the liquid molecules are sticking to each other more strongly than they're sticking to the glass. So they kind of pull in together. Concave is the opposite. The adhesive forces, the forces that cause the liquid to stick to the glass, are actually stronger than the cohesive forces, the forces that cause liquid to stick to itself. So it starts rising up the sides of the tube to maximize the interactions with that glass surface. So mostly you just need to know the definitions of these, what's on this slide. But again, keep in mind that for most of these properties we're talking about, surface tension, capillary action, it does scale with the intermolecular forces of the liquid. Cohesive forces would be the intermolecular forces themselves. It's just another term for that. Now, another property of a liquid that directly depends on its intermolecular forces is called viscosity. So the definition of viscosity is the resistance to flow. You can think about it more simply as how thick a liquid is. Um, so basically, again, this is another one where the stronger the intermolecular forces that are present leads to higher viscosity. So this picture here kind of shows the blue liquid would be relatively low viscosity. It pours out very fast. Whatever this amber liquid is, probably some sort of motor oil, it looks like, is high viscosity, meaning it's really thick, and when you pour it out, it pours out much more slowly. So stronger intermolecular forces correlate with higher viscosity, which is how thick the liquid is, how its resistance to flow. So if we were just to take three examples here of liquids and predict which has the highest viscosity, again, the real key is to look at what types of intermolecular forces they have and in which situation are the intermolecular forces stronger or weaker. As we talked about a little bit earlier, we actually gave this exact compound as an example. If you have a hydrocarbon substance, carbon and hydrogen are the only atoms in the formula. The only intermolecular forces you have are London dispersion forces. So typically when you're approaching problems that deal with intermolecular forces, the way that I think is best to do it is first think about what type of intermolecular forces they have. If you have two compounds that have the same type of intermolecular force, then you might have to think a little bit deeper about which one of those has the stronger IMF using some of the things we've talked about already. But in general, you want to first just think about what type of intermolecular force is there. And that's the easiest way to rank them if they're all different. So for this molecule here, this is called diethyl ether. It has still a 5-atom chain, but the center one is now oxygen instead of carbon. If you draw the structure of this, what you would find is that it's sort of a bent shape about the oxygen atom. Because it has the two lone pairs on oxygen, so the whole thing goes bent. So it is going to be a polar molecule because it has this oxygen in the center and a bent shape, so you're going to have a dipole that kind of goes towards the oxygen in that direction. But you also notice that this molecule does not have, even though it has oxygen in the formula, it does not have oxygen bonded to any hydrogen atoms. The only bonds to hydrogen involve carbon. So it's a polar molecule, but no hydrogen bonds that would be possible. So this would have dipole-dipole as its strongest forces. Versus the last one here, again, very similar in terms of molar weight, molar mass and size. But this time what you see is that at the ends here, we have these OH groups. So that means when you have oxygen bonded directly to hydrogen, you have the possibility of having hydrogen bonding, which is the strongest of these three IMFs. So in this case, we didn't even have to really do any more detailed comparison because we would find that this molecule here is the only one that has hydrogen bonding interactions, meaning it has the strongest intermolecular forces, and we would then predict it has the highest viscosity. All right, so that's the kind of analysis you'd want to do in most problems. For liquids, it doesn't get much more complicated than this. All right, any questions on that? All right, the last major topic we're going to cover with liquids is vaporization, which, so now we're going to give a little bit more detail, a little bit more specificity about that process of converting a liquid into a gas. So that's what vaporization refers to. It's related to boiling in some ways, but to some extent, as we'll see, it happens spontaneously with any liquid. It's not just at the boiling point that this occurs. So when a liquid converts into a gas, we call that vaporization. And the vaporization process can be described in terms of an enthalpy change. So when a liquid converts into a gas, there is going to be an enthalpy change associated with that because you have to break some of those intermolecular forces that are in the liquid to allow the molecules to escape from the surface and go into the gas phase. So because you have to break forces of attraction, vaporization will be an endothermic process and it will have an enthalpy change, a delta H associated with it. So we call that the enthalpy of vaporization, abbreviated as delta H VAP. And again, it's going to be the enthalpy change associated with vaporizing 1 mole of a substance. Always a positive value, always endothermic, because to vaporize a substance, we have to break intermolecular forces. We have to break the forces that are holding them together. So we have to put energy into it for that to occur. Vaporizing, I'll do it in the verb form. Vaporizing, typically 1 mole is going to be expressed per mole. So as I said, it's always endothermic. So condensation is the reverse process. So if you have molecules in the gas phase and they come together to form a liquid, that's called condensation. It's the exact reverse of vaporization. And because it's the exact reverse process, vaporization is liquid to gas, condensation is gas to liquid. If you wanted to define a delta H associated with that process, even though we don't usually talk about it in these terms, but it would just be the negative of the delta H of vaporization. All right, remember when you reverse the direction of a chemical reaction, you change the sign of delta H. So condensation is just the negative of vaporization. All right, so those are some definitions, and that's the enthalpy change associated with it. So vaporization leads to a property referred to as vapor pressure. So if we place a liquid in a closed container, and we saw vapor pressure a little bit in the last chapter when we talked about Dalton's law, collecting the gas over water, and then the total pressure is going to be the sum of the gas pressure plus the vapor pressure. We introduced that a little bit. So vapor pressure is that when you have a liquid in a closed container, there's going to be some pressure exerted on the surface of that container because of some molecules of the liquid escaping into the gas phase. So when you place liquid in a closed container, what happens at the beginning, there's going to be net vaporization because some molecules are going to have enough energy to escape the surface of the liquid. So eventually you're going to establish a constant vapor pressure. All right, so what basically happens is at the beginning here, you put the liquid into a closed container. All the molecules are in the liquid phase at the beginning, but then some of the molecules at the surface have enough kinetic energy that they can go into the gas phase. So you're going to get some molecules escaping the surface into the gas phase. Now, why does that happen if we're not yet at the boiling point? We'll talk about boiling point here in a little bit. The reason is because if you think about what we learned, another thing we learned in chapter 8, when you have a sample of gas, there's a distribution of molecular speeds. Some molecules are moving slow, some molecules are moving fast, and there's sort of an average value that's determined by temperature. The same is largely true in liquids. The molecules are all moving around. They're in contact with each other in this case. They're not freely moving around, but there's going to be a distribution of speeds or kinetic energy for those liquid molecules. And some of them, a small percentage, are going to have enough of that kinetic energy to be able to break off from the intermolecular forces at the surface and go into the gas phase. So that's what causes vapor pressure. Some small percentage of the molecules can go off into the gas phase. So initially, there's going to be that sort of net vaporization and the building up of the vapor pressure, but you're going to get to a constant vapor pressure because you reach what's called an equilibrium. Equilibrium is a topic you'll cover a lot more detail in Chem 2 and other contexts, but basically at equilibrium, what that means is that you're still going to have some molecules escaping the surface, but you're going to have some that lose kinetic energy and come back. So there's going to be this sort of back and forth process where in that there'll be no vaporization anymore because some molecules are escaping, but at the same time, others are coming back. And you're going to have some molecules sort of floating around up in the gas phase, causing that pressure, but there's not going to be really a net change in how many molecules are in the gas phase. If you're at a constant temperature, you're going to get to a sort of a equilibrium situation where there's no net vaporization anymore. So you can sort of describe this in a graph if you like graphs. So if you look at the rate of vaporization as a function of time and the rate of condensation, in blue, I'm going to show the vaporization rate. And that's going to be constant at a given temperature. So the vaporization rate is constant at all times, but then the condensation rate is going to increase initially because in order for condensation to occur, you need molecules in the gas phase. So at the beginning, you don't have any molecules in the gas phase, so you can't have any condensation occurring at all. But then as molecules escape to the gas phase, some are going to condense, and you're going to see this increase in condensation rate. And eventually the condensation rate and the vaporization rate are going to be the same as each other. And that's when you get to that constant vapor pressure. So that's kind of just a graphical representation of the same thing. But nonetheless, that's what causes vapor pressure. Molecules escaping the surface of the liquid going to the gas phase. In terms of how we measure vapor pressure, you can do it with a barometer, which we talked about in chapter 8. So if you want to measure vapor pressure with a barometer, you first measure the atmospheric pressure with the barometer. So we talked about this in chapter 8. A barometer is a device that's open up to the atmosphere and measures the pressure of the atmosphere. Then if you want to measure the vapor pressure of a liquid, you inject a small amount of that liquid into the barometer. Into the top part of the barometer, which is initially under vacuum. This is kind of old school and probably not super important for us, but I thought it was just interesting to know, like, how do we actually measure vapor pressure, right? So this is one way you can do it. You have a barometer here, which is just a closed container inverted into, so we have like a dish of mercury that's open to the atmosphere. And then you have a tube that's inverted into that. And the liquid rises up the tube because the atmospheric pressure is pushing down. So liquid rises up the tube to some level there and then this is the height of this is going to be approximately 760 millimeters if it's mercury. And initially this top part of the tube here is under vacuum. There's no pressure opposing that, so you're just directly measuring the atmosphere. That's exactly what we showed back in the beginning of chapter 8, how a barometer works. Then what you would do is, you want to measure a vapor pressure of a liquid, you would add the liquid to this top part, which is initially under vacuum. So then what you're going to have is the same setup, but now at the top of the tube, you're going to have some of the liquid. So in addition to the atmospheric pressure pushing down, you're going to have a new value for the height, and that's because there's going to be vapor pressure of the liquid opposing that in the opposite direction. So the vapor pressure from the liquid, which is up there, is going to push down on the column of mercury and cause it to go down a little bit. So as an example then of how the measurement works, if we have an atmospheric pressure of exactly 700 millimeters of mercury, the height that we would observe in the when we've added the liquid is going to be the atmospheric pressure minus the vapor pressure. So if we were going to do this with water at room temperature 20 or roughly room temperature 25 degrees Celsius, we would find that the height of the column drops to 736. So initially, without any water injected into the top part, it would be 760. You put in some water into the top, and the top of that column drops down to 736 because the vapor pressure is pushing down on it a little bit. So then to measure what the vapor pressure is, it's just simple subtraction. The vapor pressure would be the atmospheric pressure, 760, minus the new height, which is 736, which is 24. So vapor pressures, as we saw in chapter 8 towards the end, are pretty small compared to atmospheric pressure, but they're not negligible. For some substances, they would be higher. Obviously, it depends on the intermolecular forces you have. For water, it's at room temperature is about 24 millimeters of mercury for the vapor pressure. So then the really only quantitative thing that we're talking about in this chapter, the only equations you're going to have to deal with are the temperature dependence of vapor pressure. So how does the vapor pressure depend on the temperature of the liquid? And this kind of, again, comes down to similar things that we talked about with kinetic molecular theory of gases, where if you have a sample of liquid, there's going to be a distribution of kinetic energy or velocity. I'll write it out. It's kinetic energy, so you don't get confused about the abbreviation. So if we're plotting the sort of distribution of kinetic energy for a sample of liquids, if we're looking at initially a cold temperature, you would get some distribution like this. And let's say that this small fraction here is going to have enough kinetic energy to escape. So that's responsible for the vapor pressure, is that small fraction of molecules that have a high enough kinetic energy to escape the surface of the liquid. If we warm the liquid up, you're going to get a broader distribution, but it shifts to the right. So basically what you'll find is that at the second temperature, which is going to be the hotter of the two in this case, same axes, fraction of molecules, kinetic energy. But now what you're going to see is that a larger percentage of the molecules have enough kinetic energy to escape. As the distribution is shifted towards higher kinetic energies, more molecules are going to have enough kinetic energy to get off the surface of the liquid. So the conclusion from this qualitatively then is that vapor pressure increases as temperature increases. Right? Because the molecules will have more, on average, more kinetic energy, more of them will be able to escape the surface of the liquid. So there then is an equation that relates vapor pressure and temperature. The equation is a little bit complicated, but we're going to give a slightly more useful form of it in a second here. So the equation is that the natural log of the vapor pressure, so we haven't dealt with natural logs yet, so at the very least, make sure you know how to do that on your calculator, is equal to the negative of the enthalpy of vaporization, that's where that comes into play, over R, the universal gas constant, but expressed in joules, times 1 over temperature, plus a constant. And the constant that we have here depends on the specific substance that we're dealing with. So it is going to be defined for some substances, but it's not the most straightforward equation to deal with because it has the variable constant that we have to worry about. So water would have some constant associated with it, but a different liquid like methanol would have a different constant associated with it. In addition, have different delta H vaporization. So it's not very useful equation. But the way that we typically would use it then is to compare vapor pressures of the same substance at two different temperatures. And that allows us to derive an equation from this that's very similar, but now is in terms of two different vapor pressures. Call it P1 and P2, and that's going to be equal to, we can take out the minus sign if we want to do it this way. So at two different temperatures, T1 and T2, we compare the vapor pressures P1 and P2. Temperature has to be in Kelvin, and the value of R that we're going to use is 8.314, the other value that we didn't see a lot in chapter 8. And that means delta H has to be in joules as well. So that allows us to establish a linear relationship between some of these parameters. So if our y-axis is the natural log of the vapor pressure, again, for people that like graphs, we don't deal with graphs a lot in this course, but here's one for you. So if we plot the natural log of vapor pressure on the y-axis, we plot the inverse of the temperature on x, the slope of this would be minus delta H over R. The intercept would be C from that first equation. But what this allows us to do is if we measure the vapor pressure as a function of temperature for any liquid, we can use the slope of that to determine the enthalpy of vaporization. So that's where this is sometimes useful for us. So, and water has a higher vaporization enthalpy than diethyl ether. So water would have a larger negative slope versus something like diethyl ether, where the slope would be more gradual. Don't worry about the structure of diethyl ether, but diethyl ether is one that we showed earlier that has oxygen in the middle, but no OH bonds. So different substances are going to have different slopes, but that allows us to determine enthalpy of vaporization if we plot the vapor pressure as a function of temperature and plot it in this way with natural log for the vapor pressure 1 over T on the x-axis. All right, so as an example problem, we're going to come back to this equation at the very beginning of next time in one other slight variation, but here's one way you might see it. So we have this substance diethyl ether where the vaporization enthalpy is 29.1 kilojoules per mole. The vapor pressure is 0.703 atmospheres at 25 degrees Celsius. We want to calculate what is the vapor pressure at 95 degrees Celsius. All right. So the equation we're going to use that relates vapor pressure and temperature, the only equation you'll see in this whole chapter, I believe. It's the only one that we're going to use a lot. We can write it in, there's different ways of writing it, but if you want to get rid of the minus signs, you can write it in this way. Delta H over R, and then 1 over T2 minus 1 over T1. What you might see in some cases, I don't remember exactly how your book does it, some sources will keep the minus sign out in front of delta H, and then they'll do 1 over T1 minus 1 over T2. So it's mathematically equivalent, but it just depends on where you put the minus sign. But this is one way to do it that involves that, you don't need to have the minus sign in front of delta H. So in this problem here, we just have to define what T1, T2, P1, and P2 are. And it's kind of up to you how you do that. But let's say that T1 is the lower temperature, 25 Celsius, which is 298 Kelvin. So we'll call this T1. We'll call this T2 here, which is 95 degrees Celsius converted to Kelvin. That's 368. I'll sort of skip the math there, but that's the temperatures we need in the right units. And the initial pressure P1 is 0.703 atmospheres, and we're trying to solve for P2, the new vapor pressure at the temperature of 368. So just going to be a little bit of algebra to solve for P2 here. So P1 is 0.703 atmospheres over P2s are unknown. For delta H of vaporization is given to us in kilojoules per mole, but it needs to be in joules per mole for this because R is in joules. So 29,100 joules per mole for delta H divided by R, which is 8.314 joules per mole Kelvin. And then in the parentheses, we're going to have the two temperatures. T2 is 368. T1 is 298. And then we solve for P2. So just a little bit about the algebra. Basically, if we want to get rid of natural logs, we have to take e to that power on both sides. So numerically, this whole right side of the equation comes out to minus 2.234. And then that means if we want to, so the natural log of 0.703 divided by P2 equals negative 2.234. If we get rid of the natural log, we take the natural exponent on the other side. So 0.0703 over P2 equals e to that power. That's how we get rid of natural logs. So just a reminder of how the algebra works here. And e to that power is 0.107. So we just solve for P2 by cross multiplying and dividing, and we get that P2 is 6.56 atmospheres. All right, so that's one way we can set up a problem like this. Next time, we're going to learn the definition of boiling point and how we can then use this equation in some cases to rationalize that as well. So we'll continue with that and move on to solids as well.